A problem you might come into, and it might look insoluble at first, is this one where you've got well, one substance and another substance. The example in the book to start out is an aluminum pan at one temperature and water at another temperature. And then the question is, one's hotter than the other, one substance, but they're in contact with one another, so they will come into a thermal equilibrium. And the question is, what temperature will that happen at? And that kind of blows your mind at first, but let's step through that. It's actually pretty easy. Okay, so let's do this really general. I mean, we might have a pot and water, or any two things. And the idea is that they're different temperatures, T1, T2. They're different masses, probably M1, M2. They've got different specific heats, C1, C2, and then you bring them together into thermal contact. And so the question is, what is the final temperature? And let's give that a symbol of T sub F on there. So that's the problem statement. And how you approach this is you realize, okay, well, suppose that number 2 is hotter. It's going to have some more heat in it. It's going to give it heat to substance 1, some of it, until T1 equals T2, and that where they equal is going to be TF. So basically, this gives heat to that. So in some sense, that packet of heat that it lends is going to be subtracted from this one and added to that one. And so we didn't in the broader system here. So if we draw the system boundary around this whole thing, no heat came in or out of the bigger system. So that sum is 0. So that's my 0, and it's going to be equal to whatever heat got transferred into substance 1, and then whatever heat got transferred from Q2 like this. The algebraic sign is actually pretty important when you think about these things. So Q1 is equal to a negative Q2. So we need to actually keep that. That's the trickiest bit right there, is remembering to do this. So those bits of heat, we had this definition that the heat was the mass times the specific heat times the change in temperature, like that. And so a change in temperature is just the T final minus T initial, like that. So we can substitute this expression with little subscripts on here to set this up. So Q1 is just going to be mass 1 times specific heat number 1, and then times final minus T1, and then that's equal to negative M2 C2 T final minus T2. How about that? So this TF, that's the same. That's the final equilibrium temperature. And then this is the initial temperature, T1, initial temperature, T2 for the second substance. Okay, well, so the hard part was that minus sign. Now it's just, let's solve for TF. So put your algebra brain on, and we solve for the final temperature. Well, let's break this up. We've got an M1, C1, TF. Then we got a minus sign, M1, C1, T1. Looks like we did that well. And now we got a minus sign to start, so minus M2C2TF. Now minus times a minus is a plus, so we got a plus M2C2T2. And we want to solve for our final temperature, which appears in 2 spots. So let's add this term to both sides. So we add M2C2TF. So we get a TF. That, since we're adding, that's going to go away. So we have a M1C2 that's a C2? No, it's not. It's a C1. M1 C1 plus M2 C2. And let's add this one to both sides. So in that case, we've got a positive M1 C1 T1, and then retain this guy, M2 C2 T2. Okay, so I flipped the blocks from one side to another. So the final solution, raise the page a little bit, final solution TF is equal to that stuff, M1 C1 T1 plus M2 C2 T2 all over this stuff, M1 C1 plus M2 C2. This looks like, in fact, it is a weighted average. So we have our two temperatures, and we do this interesting thing where we multiply by weights. In this case, our M1C1 is one weight, M2C2 is another weight, and then we sum those weights up at the bottom. So if you do a regular average, you've just got T1, T2 divided by 2. So these coefficients would be 1. So 1 T2 plus 1 T1 plus 1 T2, and then you divide by 2. So that'd be 1 plus 1 is 2, 1 plus 1 is 2. Yeah, it actually works out for the regular average as well. But for weighted averages, this is how you do it. So that's the calorimetry style problem.